Okay, question 5. Figure 8 shows two magnets with their north poles facing each other. Draw the shape and the direction of the magnetic field between the two magnets. So if I wanted to, I could add the butterfly, straight, curve, curve. Obviously, that's got to be touching. Straight, curve, curve. If I did that, they'd give me the marks, but it says they want it between. So I think what I'll do is I'll leave those bits on. And now for the crucial part. So that's going to be coming from there to like that, like that, like that, like that. Now this one, I'd have lost a mark because it's not touching. And I've taught you nout and sin. So now we're just going to make sure north to south, out of the north to south, north to south. But we've got this idea that they're repelling and we've got the directions going from north to south. Okay, figure 9 shows a toy that has a plastic cylinder, a plastic base and two similar magnets. So we've got magnet 1 there and magnet 2 there. The upper magnet appears to float. So it looks like this is floating. So clearly we can see the poles are repelling each other. And this force that's repelling the magnet upwards must be equal to the weight. So we know that the magnetic force is equal to the weight of that, and that's why it appears to float. So it goes, describe the forces, use the idea of magnetic fields in your answers. So we're going to be talking about the repulsion. We're then going to talk about the forces, in that we've got weight pulling it down and we've got a magnetic force pushing up because the magnetic fields interact. So the magnetic fields interact. There is repulsion from the magnets as the same poles are facing each other. And then the last part is the weight of the top magnet must be equal in size and opposite in direction to the repulsive magnetic force. There's your model answer. Okay, next one. So here we're going to need Fleming's left-hand rule. So Fleming's left-hand rule. I would adjust my hands so that my middle finger comes that way. I'd have my first finger pointing that way, and then my thumb is pointing up. So just make sure you know how to use Fleming's left-hand rule. So which way? State the direction upwards. State the direction of the force on the magnet. So the wire's been forced upwards, and in terms of Newton's third law of motion, there must be an equal force on the magnet going down. So this would actually be an interaction force pair. The force of the wire on the magnet is equal to the force of the magnet on the wire. So state the direction of the force on the magnet. It's got to go in the opposite direction. If the wire's being forced up, the magnet will be forced down. Now, if that's on a table, then that force will be transmitted through the table. Okay, next one, we've got an FBIL question, FBIL, and it wants us to calculate the length of the wire, L. Newton's fine, amps fine, Tesla fine. So no unit changes. So L equals F over B times I. Shove in all your numbers. So 0.15 is the force. Always make sure you double check to make sure you've moved the right ones in. Magnetic flux density is that. That's that, and we've got 0.11 meters, and that's that done. That's quite a nice question.